So I hope that, sorry. So I hope now that people online also can hear us. I don't see any picture there. So if somebody could give a thumbs up from which, never mind. they might complain if they don't hear us. They should be hearing us. Anyway, welcome to Defense of Samuel Stenberg, who will, okay, good, thanks. Who will be sending his thesis, Interfacial Behavior of Ionic Fluids, Theory and Simulations. And the guy who's now standing in front of you talking is Magnus Ullner, and I will be your chairman. And for those online who want to ask questions afterwards, you have my email address here. So it's magnusullner@teokem@lu.se. So you can send me questions by mail, and I will ask them when it's your turn, so to speak. So first of all, we have to introduce the important people. For us, we have Samuel, of course, on the image. You'll see him soon. We, of course, have the faculty opponent, Mathieu Salan from Sorbonne University, Paris. Welcome, very welcome. Thank you.
Thank you.
We also have a examination committee who's sitting in front of me, and from my left, we have Maria Sammalkorpi from Aalto University in Otaniemi, Finland, in Espoo. And we have Joakim Stenhammar from Lund University. And we have Christer Elvingsson from Uppsala University. And another person who is quite important is Jan Forsman, the supervisor of Samuel. And so the proceedings for today, I will soon give Samuel the word to tell you what's gone wrong. Then we will have a presentation, a sort of general presentation by Mathieu from give general introduction to the area. Samuel will talk a little bit more about his thesis work. After that, there will be a short break, so you can stretch your legs. And then we will have question time. We start with once again, Mathieu is asking questions, putting poor Samuel on the spot. So we have a scientific discussion, we should put it like that. And then after that, the examination committee will be given the word to ask questions. And after that, it's the audience that have a chance to ask questions. And also you online, who can then send questions by email. So with that, I give the word to Samuel, who has now the opportunity to retract everything by the standard procedure. But anyway, but he should tell you a few pointers of what has happened before we start.
Turn on this, I guess.
Yeah.
Yes, so I found a few things that was wrong in my thesis. So on page 19 and equation 2.18, E should be U. And on page 22, equation 2.23, capital P should be small p. And on page 23, there's an integral in the lower limit. There should be a negative sign. Hello. No. No. I will just speak. I will speak loudly. I hope everyone can hear me. Oh yeah, true. Oh yes, and then on page 46, capital N should be capital M in the equation on that page. There's only one equation in that page. Page 71, there is surface charge should be surface potential.
So then I'll give the word to Mathieu. Let's hope that works better.
Thank you. Will it work?
No.
That's good. Otherwise, I can take them.
Maybe you need to turn that one down.
It's off. Okay, somebody has muted them.
Okay.
Okay, so does it work now?
Yes.
Okay, perfect. Thank you very much. So I'm very happy to introduce this PhD defense, and I would like to thank Jan for inviting me to do this job. It's the first time I'm the opponent here in Lund University. So today we will talk about interfacial behaviors of ionic fluids. And this is a topic of great interest for a lot of applications. You can find such problems in conversion, for metal, nanoparticles, and a huge variety of things in chemistry. But the focus in the thesis and the field in which I'm more specialist is energy storage, and more precisely the use of supercapacitors. So these are devices that are not so well known compared to lithium-ion batteries, because they are less used, of course, but they have some advantages. And so on this plot, you have the specific power versus the specific energy. So if you think of putting the device in a car, the specific energy will tell you how far you can go. So you go much further with lithium-ion batteries. But the specific power will tell you at which speed and at which pace you can discharge a device. And then you can see that supercapacitors are in between these lithium-ion batteries and capacitors, which are used in conventional microelectronics. And so this makes them very appealing for a range of applications. An important aspect to take into account is for these devices that compared to batteries, they have a much better lifetime, which we measure in terms of the number of cycles of discharge that can be done. So this is a typical bottleneck of batteries that have to be changed after, say, a few thousand of cycles. But supercapacitors can run for millions of cycles without being damaged, and this makes them much more reliable for some applications. And you can immediately see one example where this is important. So for you, if you look at aviation, aeronautics, you need the planes are more and more electrified. And we could hear this in the news recently over the past 10 years because some planes were stuck in airports because of this, because of problems with batteries and so on. But with supercapacitors, there are no such problems. So they cannot be used for the same things. But in the example of the Airbus A380, they are used for the opening of the doors. So this is something where the door is very heavy, so you need a lot of power to open it. And so this is why they use supercapacitors. And you will open the doors of the plane very often in its lifetime. So having a good cyclability is very important. Then the second application is for energy recovery. Because if you think of, for example, in the left here, you have a crane, so which will lift a mass on a very short amount of time. You could use a battery to recover the energy when the mass is going down. But the problem is that you will not charge it very much because if you charge a battery very fast, you damage it a lot. So this is an example of potential energy recovery that is quite important in industry. But much more common are cars. And so you can see that supercapacitors are also used in conventional cars. They are used to recover the braking energy. So when you brake, it lasts for a few seconds. There is a friction. And you can recover this into a supercapacitor and you reuse it. And that's called a stop and start system. And then they can also be used to completely power electric vehicles. So here you have examples of bus. And of the second picture is a boat in France. So the idea is that with a supercapacitor compared to a battery, you will not do 100 kilometers or a few hundred, but you can do for sure 1 kilometer or 2 kilometers. And so if you can charge at every stop, so for example, the bus, every kilometer you discharge passengers, so at the same time, you can also discharge electrons or charge electrons. And for the boat, it's the same, it's just doing round trips in a small harbor. So you can easily charge and discharge it during that time. So you can see that, of course, the market of supercapacitors is smaller than the one of batteries, and there is no way it will be a competitor, but it's really a complement, and it can have some very important applications in the future. So now let's move to more science. So this is a schematic of a supercapacitor. So you can see that it's made of two electrodes, which are usually made of porous carbon, but new materials are also emerging. And in between, we put a charged liquid. And the idea is that this device is not charging through chemical reactions, but through physical adsorption. And this is why also you have a big, good cyclability, is because you don't have any irreversible chemical reactions. So the two main properties are the energy density, which is given as a capacitance times the voltage square divided by 2, and the power, which is the voltage divided by 4 times the resistance. And what appears that in each of the 3 characteristic quantities that are involved, the capacitance, the voltage, and the resistivity, the electrolyte is playing a very important role. So it will impact the capacitance because this depends on how much the ions adsorb on the surface. It will impact on the voltage because this depends on the stability of the liquid under electrochemical reactions. And it will depend on the resistivity will depend on it because this is a dynamic property which depends mostly on the diffusion of the ions. So we need to understand well how the electrolyte is behaving in such devices. The problem is that this is a simplified picture, but already we have a lot of different parameters to take into account. The surface area, so you see here, the structure of the electrode is very complex, and in fact, you could fit a surface of the size of a football field in a very small piece of carbon. And so you have to take this into account. The ion size, the size of the pores inside the carbon structure and how they match is also important. I will go back to this. And the concentration of the electrolyte is also something that could play a role on the performance. And so this means that it's not possible to do experiments on every single electrolyte and every material and test which one is the best. So this would take decades. So we need to have computational tools to guide the experiments toward better supercapacitors. The problem is that simple theories are not very well adapted to this challenge. In the field of a metal electrolyte interface, there is a very famous one that now dates from 1 century ago, which is due to Gui, Chapman, and Stern, and explains in a very simple way how the ions will adsorb on the surface. But it has a lot of issues. There are a lot of effects that are not taken into account, and I guess that we will hear about this a bit much later. So it cannot be used very efficiently for the systems we are interested in. And in particular, one important effect is that the system is concentrated in ions, and ions interact a lot with each other because of the Coulombic effect. So there are strong repulsion between lightly charged ions. There is strong attraction between cations and anions. And so this correlation is important. And this is something that we need to take into account when addressing the problem. And here you have a picture of X-ray diffraction from a paper of Mesger, where you show cation and anion arrangement that are strongly entangled at a charged surface. Now, a second important aspect that I already mentioned is the fact that we deal with nanoscale effect. And so here, this is results from a paper that really changed the field 15 years ago, where it was shown that when the pore of the carbon structure are below 1 nanometer and close to the size of the ions, there is a strong increase in capacitance, and this has really driven a lot of research, both from experiments and from simulation. And as soon as you tackle with, you're tackling a nanoscale effect, it means that the molecular aspects become important to be taken into account, and you need to go to the microscopic scale to fully address them. So this leaves us with one solution, which is molecular simulations. And again, we are facing some important challenges. Here, I really simplified a lot the picture, but even there, we can see that there is a strong difficulty, because on one side, we have charge carriers, which are electrons, and the dynamics is governed by quantum mechanics. On the other side, we have ions and solvent, in which, of course, quantum mechanics can play a role, but we know that, in fact, in most of the situations, everything can be handled well at the classical mechanics level. So we have two systems that are more straightforwardly described with a different field of physics, and we need to combine them together. So there are a lot of groups that are doing this right now. I think it's a very important topic in the physical chemistry literature. Here we will focus on only one side, which is to try to simplify the quantum mechanics side and to put it in a classical mechanics framework. And so we go to the field of constant applied potential classical simulations. And so in short, the idea is to reproduce the polarization due to the ions on the surface of the metal. And this is what is represented here by the blue spheres and the red spheres on the two sides of the simulation cell. And so now we go back to the title of this PhD. It's Interfacial Behavior of Ionic Fluids. So I think today we will hear about a lot of different topics, but in my opinion, the most important things we will discuss are how can we efficiently handle the computation of the electrostatic interactions in the system. This is a difficult problem in physics, and we will discuss about this later. The second thing is that to simulate correctly the system, it is adequate to control the chemical potential of the ionic species, and this is not something easy, and that's something that has been tackled in Samuel's thesis. What are the effects of the ion-ion correlations on the wall-wall interactions? This could seem surprising, but in fact, due to the fact that the ions will interact with each other, the surface can attract or repel each other or not even interact, and that's something that will also be discussed. And finally, there are some recent reports, and including in this PhD, on the existence of phase transitions in the liquid. They can have a large impact in capacitance, and I think that could be a very important topic in the future of this field, and it will be important to discuss it today. So now I'm done with this introduction, and I'll leave you, Samuel, to get started with your presentation.
Thank you.
Thank you very much. So now we will move over to Samuel to give his presentation.
Thank you for the nice presentation.
Okay, now I have to find this one. I have to share my screen also, right?
Yeah. Försöka flytta den där som säger att det pratar också.
Ja.
Den, jag flyttar på den.
Den här jag kan.
Mm. Exakt.
Okay, so thank you everyone for coming to my defense, and welcome. And yeah, thank you, Mathieu, for that nice presentation. So yeah, the title of my thesis is Interfacial Behaviors of Ionic Fluids, and this seminar I've divided into 3 parts, if I'm able to switch. Whoops. I should put it in some kind of, yes. Does anyone know how to do this? Single page? No? Oh, yes. Perfect. Okay. So yeah, interfaces of ionic fluids. So I divided into 3 parts. So first, a very, very short introduction. And then I will come to the 2 main topics. The first one is electrostatics. And the second one is the interactions between charged surfaces. So first, a very, very quick introduction. So in all of our simulations, we treat our ions or our molecules as spheres. And there are some good things about this, and there are some bad things about this. Of course, we have, and they also have central charges. So we have removed all of the internal degrees of freedom. So this means that it's much faster to simulate, of course. And also it's much easier to elucidate mechanisms behind different behaviors. But it also has some downsides, right? Because molecules and ions, they do not look like spheres. So it's harder to compare to experiments. And also for the same reason, we don't use we don't use explicit solvent. The solvent is always implicit. So with that, we start with the first topic, which is electrostatics. And the problem with electrostatics in molecular simulations is that it's long-ranged, and we can only simulate small systems. So what we usually do in molecular simulation is that we take our box and then we replicate it in space everywhere. And then we simulate our central box, and while all these particles interact with all the replicas, which in principle creates an infinite system. And this is also a problem because it's very hard to sum, because then we end up, when we calculate the energy of this system, we end up with this infinite sum that we somehow have to calculate. And the common way to do this, or the most accepted way maybe to do this in molecular simulation, is to use E-wall summation. So in E-wall summation, we add and subtract a screening charge distribution to our charge distribution. So let's say that, let's call our charge distribution rho, and then we subtract a charge distribution G, and then we add it back again. So in principle, we haven't changed anything, right? And then we call this part the short range part, and this part the long range part, and it will become apparent later why we call it like this. And in E-wall summation, this screening charge distribution is a Gaussian. So it looks like this. So on this part here, we have rho again, which is our charge distribution. So we have two positive charges and a negative charge, illustrated by these point charges. And then we have this term, which is this charge distribution minus our screening charge distribution. You can see these Gaussians then screen these point charges. And then we add it back again. And this is then the form of a Gaussian function, where sigma here is the width of the Gaussian. So if we put this charge distribution into Poisson's equation, because we want to calculate the energy of the system, so then we need the potential. So if we put it into Poisson's equation, we get this kind of potential, where this is the complementary error function, and this is the error function. And we again see that it's dependent on sigma here. And this complementary error function, this converges nicely, and the convergence is then also dependent on this width of the Gaussian, so the sigma. And then we have this error function, which does not converge very nicely. So this we have to solve, and this comes from this short range part, this complementary error function. So since this does not converge very nicely, we have to do something else. So then we take this, and we instead solve it in Fourier space. So we make a Fourier transform, and then we sum over all of these interactions in Fourier space, and then we transform it back, which then converges much better. But this converges nicely, I said, but we still have to have some form of cutoff somewhere. We can't sum to infinity, so we have to have some type of cutoff. So this is so in our first paper, we did the same thing as in E-wall summation, but instead of these Gaussian functions, we used truncated Gaussian functions. So this is the same image as before, but here you can see that these Gaussian functions, they are truncated. But then we do the exact same procedure on here. So this dotted line here is a normal Gaussian, and the full drawn line here is the truncated Gaussian. So if we make the exact same procedure, we end up with a short range part, which looks like the fully drawn line here. And the dotted line here, this is for normal E-wall summation. And we can see that we need to use a cutoff. And the energy will not be zero at the cutoff, so we will miss a bit there. But if you use these truncated Gaussians, the energy is always zero at the cutoff. And this is good because the function is smooth, so the forces does not diverge. So it's easy to run molecular dynamic simulations of these. Because the forces does not diverge at the cutoff. And also, as I said, the convergence in E-wall summation depends on the width of the Gaussian. But in our method, it does not, because the energy is always zero at the cutoff. So it's independent independent on sigma. So to test this method, we calculated the energy of a face-centered cubic lattice of a unit cell in a large crystal. And this energy you can calculate analytically. So then we compared our method with normal E-wall summation, and we calculated the energy of this face-centered cubic lattice. And these are the results for this. So So this figure is using our method, and this figure is using normal E-Wood summation. And bright colors here. So white is a small error, and black is a large error. And on the x-axis here, we have the real space cutoff divided by sigma. And on the y-axis, we have the long-range cutoff, or the reciprocal space cutoff. And we can see that using our method with either a very short cutoff or a very large sigma, so a very wide Gaussian, we can always retrieve the correct energy. While using normal E-Wood summation, we get this short-range cutoff, or a cutoff area in the short-range part, which we can never retrieve in the long-range part. So this was the first. Paper, and this is of course for bulk systems. But then we're also interested in systems where we have a charge, and then in the presence of some polarizable surface of an electrode. So this is meant to illustrate a system where we have a positive charge here, and this thick line here represents the interface of an electrode, which is infinitely conducting. So that means that the dielectric constant inside the electrode is infinite. So here is the electrode. So what happens then is that this charge will polarize the surface, and mathematically we can represent this polarization as an image charge here. So that we can say that this positive charge generates this image charge, which is a representation of the polarization. So this is a fairly simple case, but then if you have another surface here, the situation gets much more complicated, because then this charge will again polarize this surface, but this image charge will also polarize this surface. So this creates this infinite array of image charges in this direction normal to the surfaces. So this we have to somehow take into account. So what we did is that we constructed a special type of unit cell. So let's pretend that this C0 is our unit cell with some positive and some negative ions. And then we reflect all of these ions through the left surface and through the right surface. So we get these primed systems here. And then we cut these in half, and we end up with this system. And if we take this system and we replicate it using E-Wood summation, we end up with the exact system that we wanted to get in the previous slide, with these infinitely polarizing surfaces on each side of the box. And there are some benefits of this method, and that's that electroneutrality is always maintained. So that means that we can run grand canonical simulations with single ion insertion. So we can insert a cation, which is not possible in for instance, normal when you run normal bulk simulations, because then you get a charged system, which is not allowed. So electroneutrality is automatically maintained. And this also means that we're able to run simulations at constant applied potential. So we have a box, and then we have some electrodes, and then we can apply a constant potential across this electrode, which is in contrast to constant charge simulations. And it also turns out that using this method, we're able to calculate the individual chemical potentials of the ions. And we use this fact to evaluate our method. So the red line here is the value that we calculated for the chemical potential of the cation in some system. And then this is for the anion. And then this black line here we ran bulk simulations without E-Wood summation, but just with a minimum image truncation. And this is increasing box size on the x-axis. And we used a modified Widom technique to calculate the chemical potential. And we also used some other methods to evaluate our method, but they're a little bit more involved. So I'm only showing you this here. So now we come to the second topic of the thesis, which is the interactions between charged surfaces. And these, as we also heard from Mathieu, they exist in a lot of different contexts, like the interactions between large particles in solution, for instance, and in supercapacitors. So here we consider both conducting and non-conducting surfaces, and we also consider a constant charge and a constant potential ensemble. So in the third paper, or the first paper for this topic, we study the interactions between non-conducting surfaces. So we have a simple salt with a multivalent counterion to the surfaces, and we have these two charged surfaces. So this system has been studied before, but the focus has then been on the interactions at short range between the surfaces. We instead focused on the interactions at longer range. And what has been found is that in, for instance, some colloidal dispersions, if we have a low salt concentration, they are stable. But then as we increase the salt concentration, the dispersion gets stabilized. But then if the salt concentration is even higher, it's stable again. So we wanted to see if we could see this in the simulations. And explicitly, we wanted to find if there is some direct connection between the overcharging of these surfaces and the free energy barrier between the surfaces in the interaction free energy. So this is then so on the y-axis here, we have the integrated charge. So here is the surface. And then on the x-axis, this is the coordinate normal to the surfaces. So this is into the box. And we can see that if we have a high salt concentration, we have an overcharging where the counterions effectively overcompensate the inherent charge on the surface. And then if we have a low salt concentration, there is instead an undercharging because there's not enough ions to screen the charge, to screen the surface charge. And if we have this intermediate concentration, there is this perfect neutralization. And this is exactly what we see in the interaction free energies also. So we see here again that if we have a high salt concentration, we find this barrier. So this is the interaction free energies between the surfaces. We see this barrier, and with this intermediate concentration, the barrier is removed, which then means that it will be destabilized. And this is with the Monte Carlo simulations. And then we also did the same simulations with a correlation corrected Poisson-Boltzmann approach, which in principle is like Poisson-Boltzmann, but we also add some correlations between like charged species. And then we see qualitatively, we see the same results. And then if we remove the correlations, all of these effects disappear, which is this one. So in the next paper, we did the same study, but instead we studied the conducting surfaces. So here we were interested in the same things. So we did the same study, and we in principle found the same kind of behavior also. But we also found that if we look at this bottom graph here, we found that the magnitude of the overcharging is a non-monotonic function of the surface charge. So if we have a very low surface charge, we get this overcharging, this black line here. And then if we increase the surface charge, the magnitude of the overcharging is decreased. And then if we increase it even more, we increase the overcharging again. So it's a non-monotonic function. And then again, we saw we saw the same things as we saw with the non-conducting surfaces, that we find this intermediate concentration where the surface is neutralized, which in principle removes this the interaction-free energy barrier between the surfaces. So there's many problems with these polarizations of the electrodes. The situation that I've talked about so far is with planar surfaces, but if you have curved surfaces, it's much more complicated, because then you can't use these simple image charges anymore. So for instance, if you have metallic particles in some solution that are approximately spherical, this is very hard to handle. So what we try to do is that we try to remove these image charges and instead use this kind of effective potential So each ion interacts via this potential with the wall instead of with these explicit image charges. And this then the charge or the valency, and then we have the diameter of the particle, and then this is the coordinate then. So, and this AW then is a fitting parameter which you fit for your system. So we tried using this on a system, and we calculated the pressure normal to the surfaces. And so this black line here, this is with using the method that I've been talking about so far. And then we tried instead this method where we have fit AW, and we get this green line. And we can see that it fits very nicely and seems to work very good. So yes, and then the final paper in which we studied a similar system, but in this system we see that as if we have so we have a simple salts confined between two surfaces, and at a low surface charge, with the solution is pretty dilute. But then if we increase the surface charge, we have a phase separation into a much more dense phase. And we studied this using both constant charge and constant potential simulations, and with and without conducting surfaces. So the first thing that we found was that using conducting or non-conducting surfaces, it didn't make much of a difference. We saw kind of the same thing. So here I will only show results for non-conducting surfaces. So these are the results for a constant applied potential. And what we can see that, so this is the separation between the surfaces. And on the y-axis here, we have the surface potential. And on the x-axis here, we have the surface charge. So the derivative of this curve is in principle the capacitance. So what we can see at larger separation, we see this phase separation. So as we increase the potential, the system will jump. Or rather, we start with the dilute phase, and then as we decrease this, it will jump to the other phase. And as we decrease the separation between the surfaces, this phase separation disappears, and we get into this more critical regime where we have this gradual change instead between the two phases. And for the large separation, we can even get this hysteresis effect, where if I take this a configuration from this simulation, and then I run it at a slightly lower potential, I can get this point, and I can continue this, and then at some point it will jump to the other phase. And then instead, if we run the simulations at constant charge, we get a different behavior. So here at large separation, we can see this phase separation again. But then as we come into this critical regime, which is this black and blue line here, we can see that the phase separation disappears, and we instead get these regimes with the negative capacitance. And this has been debated, like when does negative capacitance occur and under which conditions. So here we find it in this kind of these critical regimes. And thank you for listening. Yeah. Thank you.
So that was the introduction part. Let's see what the time is. So we are now 5 to 10, and I think we have a 10 minutes break. So we will resume 5 past 10. Stretch our legs and get some air or something. So, yeah. And then you're all welcome back, of course.
If you want.
If you're, yeah.
Tänk vad det syns ut. Ja, okej. Ah, ja, det får gå. Det får gå. Ja, nu slips då. Nej, jag kan inte andas.
Jaha.
Jag kan inte andas.
Ja.
Nej, nådigt svettig nu kan jag säga. Ja, det var det lätta.
Det var jättebra.
Det var det lätta också.
Ja, men det var verkligen. Jag tänkte från igår. Det var liksom...
Ja.
Vill du ha lite svart? Ja, men tack bara. Massa.
Titta på dig själv sen också.
Vad sa du?
Titta på dig själv också.
Ja. Va? Ja. Jag får göra det sen. Jag gör det sen efteråt.
Vi kan ställa oss och ha en autograf.
Ja.
Jag får tillbaka. Jag trodde du skulle gå.
Ja, just det.
Ja, det finns en sån där automat också man vill köpa. Man vill ha något. Ja, just det.
Det verkar inte alls vara.
Okay. That's good. I am dying inside.
It's not visible at least.
Säg ja.
I will try. But it went better than I thought. I will practice with.
Really clear with the indication.
Yes.
That's good. I practiced with Josephine yesterday, and I stumbled a lot.
Okay.
But no, it was better now.
And now it was nothing, no stumbling.
Yeah. Here comes the hard part.
It will be fast.
Yeah.
Just think about tonight we are going to run in the garden searching for
Snails.
Yeah.
Now I will.
Talking about frogs.
yeah, exactly. Yeah. Yesterday I found a big snake. Oh my God, yeah.
Leapfrog integrator.
Yeah, exactly. Leapfrog, yeah. Yeah, I'm still envious of you guys who are done.
Oh, you're almost there yourself.
Not close enough, it feels like.
Nice to have it in the morning.
Yeah, in one way, but I mean, I slept like 2 hours, I think. So yeah, so this is not good. I mean, and I was super stressed when I woke up. I was like,
yeah. It's always like that. You're so afraid of oversleeping.
Yeah, exactly. Yeah.
I think you're going to sleep for like 12 hours tomorrow.
Yes, yeah. I mean, I think I have to. So we're going for lunch afterwards, and then I think I have to sleep a few hours before the part. Yeah, exactly. Yeah.
Oh, this one. Ah, that one. Yeah.
Should I have the mic on? No, we have both mics on, like that one, but that's only for the committee,
audience
I guess.
and committee. Yeah.
Oh,
Yeah, there's always a problem with the mute button at my defense. But
yeah. Yeah, I never understand how this system works. I mean, it's too many buttons to press.
Exactly.
It should only be a start button.
Exactly. Okay, Stefan's comment.
Walk into the picture. So yeah, welcome back, everybody. And now we have question time. So we start with here. You have all the time in the world. Lots of questions. We hope you don't stay all day.
Oh, sure. So, again, I was very interested in this format. I think it's very nice dissertation that you made. I must admit I had more than 30 questions at my first reading, but now I selected the most important ones and to be shorter than this possible. So I would like to get started. So first with the model that you use. In your opinion, to which extent can capacitors be simulated by simple pores like this? So you have slit pores separated by a flat surface. So how strong do you think this is an approximation?
Yeah, I think it's that's a good question. I mean, of course, does this work? No?
Right.
Yes.
Yeah.
No, but it's
Low voltage.
I go anyways. Or yeah, I mean it's. I think of course these real pores they can be like cylindrical pores and have different shapes. Yes, so but I think we can find like some fundamental mechanisms. I think we can find with these slit pores. I think, but then maybe like to calculate the real capacitance, like to do quantitative. I don't think we can like compare quantitatively, but some qualitative behaviors. I think.
Yes, so there is a question of the shape of the pore, of course, but also the fact that they are adjacent one with each other. And do you think also this can impact a little bit the results?
Yeah, maybe. I think they're also separate. You mean the anode and cathode?
No. Even in a single electrode, if I go back to your picture, it's page 70, where you have put this picture of for this electrode, and you can see that the pores they are close to each other.
Oh yeah. Yes, this is true. Yeah. This can also this will also probably have an effect. Yes.
So, do you think it could be a strong effect?
I mean, I don't know. We haven't looked into it, and I don't know if I have seen. I don't think I have seen so many articles that investigates this. I don't know. I mean, for the systems that we investigate, I don't think it would have a strong effect. Maybe if you have a more realistic model of a capacitor, maybe it will have a larger effect.
So then, still about the model, I have a question. So, yeah, you talked about anode and cathode. So, just I want to be completely sure because you've shown all your results on one single interface, or almost all of them. But in your setup, the two electrodes or the two walls are the same potential, right?
Yes.
Okay.
Yes, exactly. Yeah, so we only have one.
Yes. So it's an effective setup to simulate single electrodes at fixed potential, but not to simulate a capacitor with an applied potential.
Yes.
Okay.
Yeah.
Okay. I wasn't sure. I think it's an important difference, and it's very useful to do this because we can take a lot of information of it.
Yes.
But yes, because there is always a question of this reference potentials, and because when you apply a potential to the two electrodes, that's a quantity that you fix, and you don't really care where the liquid goes because you have two boundaries. In your case, you fix the potential between the electrode and the liquid.
Yes.
And so in your thesis, you discuss a lot about the reference potential.
Oh, yes, yes.
And but you didn't tell about this today. So my question is, how much this reference potential would change if you change some details of the model? Imagine you take something more complex and a direction constant for the solvent. Do you think there would be large difference in the various potentials that you measure in the simulation, or?
No, I think I might have misunderstood you first. So this reference potential is this because we have a potential that we call the reference potential in paper 2. Is that the one?
Yes.
Yeah, okay, so this is a potential that measures an electrostatic asymmetry between cathodes and anions. This is okay. Yeah. So what was your question?
So my question is, because I'm more familiar with full molecular models, and I know that, for example, if I change my potential for water, I will change my liquid potential. So I'm wondering if this would be the case also in a setup. Do you think it will? I know it's a bit beyond what you did in your thesis, but since you discussed this.
Yeah. So you mean if I change the electrolyte or the salt, if this changes this
So not well, the way you represent the solvent mostly, because the salt.
Okay. Yes. Yeah. I mean, yes, it would change because it would definitely change if you. I mean, if you make any change which has some change in the electrostatics, this reference potential changes. But how much I don't know.
So in the end, this reference potential is a feature of the model, right? It's
I mean, it's more like it's because so if we have for instance a symmetric solve, completely symmetric, so it's a 1-1 solve with the same size and everything same, then the reference potential is 0 because then we have both the anion and the cation has the same chemical potential. So then the reference potential is 0. But then if we make one of them divalent, for instance, then there will be a finite reference potential, which then incorporates this asymmetry, which takes into account that the anion and cation does not have the same chemical potential. Yes, and then this reference potential, because when we apply a potential between the electrodes in our simulations, and we apply this potential which we call the bias potential, but we have to relate the potential that we apply in simulation. This we have to relate to the surface potential, and since the surface potential is measured in relation to bulk, like with bulk with the bulk solution as a reference, then we have to subtract this reference potential, and this we show in this paper too.
So since you mentioned multi-valentines, you have a lot of results with divalent and trivalent ions, so something with tetravalent ions at some point you mentioned.
Yes.
So indeed, I think it's useful because it can bring you some, well, you bring a strong asymmetry in the system, so you can see more physics.
Yes.
What is the strong approximation you make? In particular with trivalent ions, do you think that the model is incorporates everything in such a case?
Strong approximation with trivalent ions. I don't know actually. I can't think of anything that's more an approximation than for monovalent.
Well, you will have a very strong, they have a very strong polarizing power.
Yes.
So, and the solvent treated.
Oh, okay. Oh, yes. Okay. Yeah. I see. Yes. This effect will of course be larger for more trivalent ions than for monovalent. Yes.
And do you think there can be ways to tune this in such primitive models, or it's a very hard task?
So to tune the
I don't know, for example, by accounting for this strong hydration in the short range potential, or by something a little bit.
Okay, the strong hydration. I mean, we tried one model in which the So in solution, the cat ions had one radius, but then they could penetrate the wall of it, and this would then model that the water or the hydration disappeared when they come close to the wall.
Yeah.
I mean, this might be one way to model this a bit.
Because the radii that you use for the ions are quite charging, right?
So what?
The radii that you
Oh, yes. So normally I think we use 2.5 angstrom, and 2 angstrom, I think.
it may account a bit for, or maybe also a way to effectively have a kind of relationship. It will depend, of course, on the species.
Yeah.
Okay.
Yeah, but it's a good point. It's a good point.
Okay. Okay. So now let's switch to the first part of your presentation today, the summation method. So I'm very interested in this because developing myself some of these tools for molecular systems. And our computers spend all their time computing these electrostatic iterations, so we need to be efficient.
Yes.
So first about the method. I think an important, that's something you started to address a little bit when you discussed the flat versus spherical surface. Do you see a way to extend this image search method to include some chemical information about the metal? So for example, if someone wants to compare gold and platinum, which have different surface and contact, or different faces of gold, do you think it would be possible to do it? Or
We thought about this a little bit. We also thought about different, like not perfectly conducting, also different types of constants.
yes.
But this, with our approach, I mean, there might be a way, but we haven't figured it out, because the problem if you have different dielectric constants is then it's not the interactions are not symmetric, because they will decrease with a factor the further into the electrode you go with the interactions with the image shorter. So we haven't figured anything out this. And then as soon as the surfaces are not flat, it will not work anymore either, right? What was there another question?
No, we were. I think it's and also the other one, because I was also wanting to ask you about the screening, whether it was possible to tune the screening inside the metal. But,
yeah, unfortunately not. I mean, we thought about it a bit because it would be very interesting to investigate these cases also. But yeah.
Yeah, I guess that was a 3D periodicity and stuff. Very tricky.
Yes.
Are you aware of this very recent work from the group of Bokeh? So they have made a fluid. So the electrode is a fluid which free of charges. So it looks a bit like a plasma that will respond to the electrolyte charges by moving and by accumulating on points where you have capacitance and ions. And I was worried. I don't know. You are not aware of this, right?
I'm not aware of it, but we actually tried something in quite early when I started. We tried something, and I can't remember how it went actually. But I remember one problem is if you want to have a constant potential, this gets very complicated, because then you have to have some kind of procedure to keep the potential constant, and then you have to either change the charges of you have to change the charges of these wall charges, which can be take a long time.
Yeah. So yeah, but I was asking because I think that could be interested in a method with a really very model conditions. I don't think they did anything special for the moment, but maybe they can look at it.
Who was it?
It's Ionic in Paris, working this kind of mostly trying to use the screening. That's his objective, but in the end, it could be interesting by the method. So this was mentioned. I did not have time to check in the literature. So So when you do this method where you double the system of alpha on each side, and then you can do the 3D PDC and it works well. I wondered what becomes the unemployment for the system. So because you have your system has n particles, but then you have n particles which have no mass, if I'm not wrong. Or I'm not even sure because I see that.
And I planned to say this, but I forgot during my presentation. But yeah, because when we replicate this system, we get terms that we don't want, because we don't want the internal image charges to interact amongst each other. But it turns out that it's very, very simple, because in principle we only have to divide the energy by half in the end. So we take the equal energy that we get and we just multiply it by 0.5 and we get the correct energy. And that's because of the symmetry in the system. And yeah, so when we do this, we remove these internal interactions inside the electrode.
Well, for the energy, I completely understand the procedure, but my question was more, what is an internal system in terms of how many degrees of freedom do you have? Because again, you have n particles or 2 n particles.
I mean, we have. There's n particles. There's n particles that are free to move, so to speak. And then because the image charges are completely correlated to the movement of the other ones. So I mean, we have. Yeah, it's in that sense it's n degrees of freedom because we have n particles, and the other ones we can treat them as like an external potential or something like that. Does it answer your question?
Yeah, it's not very easy to model. And then, so this is implemented in a code that you have developed here, right?
Yes, exactly.
Yeah. Because then I have one thing I'm wondering is, of course, the computational speed up is clear, but there is also computational complexity. When you start, imagine you want to implement this in NAMS or any other molecular dynamics code, then this goes completely out of what the code knows to do, because there are additional particles that are non-interacting with what you said. You don't want them to interact. Yeah. So how much more complex is it to have this in the code?
So I would say, so my code is not the best to measure with, because it's not very optimized. Not compared to professional codes. But I mean, the complexity should be the same as in normal Ewald summation. I can't remember what that is in your case, but it's like n to 3/2 or something with optimal parameters. Because the only thing that you do is that you add these particles, right? So you get maybe you get 2 and I don't know.
Yeah. My question was not more on the mathematical complexity, but on the computational complexity, because you introduce additional objects, additional coordinates. So volume of the supercell is also quite different. So I guess this can be not so easy to implement in.
Oh yeah, I started to. I started to implement it in a program recently, in another program, which also exists in the division. And it might be that program is very well structured, but it was not so complicated actually, because then I mean the volume is pretty easy to just double the volume, and then in the I mean I guess it's a hard. I think it's hard to. It's a hard question because I think it depends a lot on how the program is structured from the beginning. If it's very well written, it will be very easy to do it. But if it's not well written, it's going to be very, very hard.
But one difficulty I see, for example, is so you are with small systems, and so you don't really need to use the computers, for example. But imagine you want to apply this to a huge system, and then you need a very well parallelized program. And so whatever requires program is good at doing stupid things. But
Yeah,
for
yeah.
example, you want the image charges not to interact with each other, and this starts to be a bit too smart for parallelization. So that's why I was saying it. But that's
and this, you might be right. You might be right. I imagine this can be very specialized software.
Okay, so now I have a question about I wondered a lot about electron neutrality issue when I'm reading your dissertation. An important question, so that we also face when we do this when we did this, such constant potential simulations is whether or not we should allow the total charge on the electrode to fluctuate, but we are dealing with two electrodes with opposite signs, so it's a different point. So you have a single electrode, and you have the charge is fluctuating to total charge.
Yes.
Is fluctuating to compensate insertion or deletion of ions into liquid when you work canonical Monte-Carlo. Is there maybe there is I want to go back and do another time. So it means that you are in some way also doing rank canonical in the electrode charge because you exchange with a system in the exterior. So do you have is there a term corresponding to the chemical potential of the electron or of this additional charge? Is it in the bias potential? Maybe it's in the bias potential.
That I don't know actually. I don't know this. I haven't thought about it.
It's it's because I was asking this because that's something we have to face.
I think I see your. I think I understand what you mean. I don't know.
But I think it may be, in fact, what you call the bias potential could also be called the chemical potential of the electron that you exchange. So that's something to check.
I will definitely think more about it.
Then still about the grand canonical setup. So just to be sure, when you do insertion or deletion of ions, do you have a seven system with which they are in equilibrium, or?
I mean, we have some kind of bulk, so it's an infinite bulk.
Infinite. Okay. And so for this one, you know the chemical potential.
Yes.
Okay.
Yes.
All right. Well, a simple question. Because there are ones a little bit. Page 36, something that I noted is when you, and also you mentioned it today, when choosing the cutoff, this expression 3.16, is it really divided by RC or is this a typo? Because in the page after you say sigma is chosen, so the value of the factor usually on the order 10 to the power minus 6 to 10 to the power minus 5. So
okay, there might be some inconsistencies. So the 3.16, this is the short range potential at least, because this is so then this is like proportional to the value at the cutoff. 3.16 is proportional to the value at the short range cutoff.
mm-hmm.
And then so then I write something else in.
Well, in the other page there is not the factor 1 over S, so that's why I was wondering which expression was the good.
Oh, but there is. Do you mean that in the middle of the text on 37 or?
Yes.
But there is a 1 over R there, right?
Yes, but it's also in 316.
Yes.
I think it's mostly details.
Oh, wait, I missed. Okay. Okay, yeah, okay, there might be some error there. But, yeah, I can see it now.
No, I don't think it's a very important point.
I would, yeah, but yeah, the point was like because it can be quite hard to choose this cutoff. I think it's nice to have like a general value that you can almost always use.
Yes. Yes. Well, I agree with it. It's always fun to choose this kind of parameters.
Yes. Yeah.
Since we are on page 36, I also noted there is this figure. If you have a figure with units and to give precise numbers, it's always better than dimensions like this. So.
Yes. Yeah. You yes, I agree. And when I see it, I regret my choice not having it.
Okay.
Yeah.
That's a good issue.
Yeah.
Okay. So. So I noted figure 6.4, but I don't remember which question I had about this one. Okay. Yeah, it's one about, you also showed this part about the surface charge depending on the apparent charge depending on the surface charge. And so you have very strong differences there. And I was wondering, so you have usually when we see some behaviors that are more like the one above, where you have some peaks growing or decreasing, but usually they come at the same position. But here you have also the displacement of the peak. So if I understand well, this correct, this is because at some point you degrade in one type of ions, and that's why now you have a shift of the peak.
Sorry, I didn't understand.
So, for example, if I take the purple and the green, so the peak position is moved by 5 angstroms more or less.
Yes.
So I guess this is due to the fact that in one case you have a layer of ions that has disappeared in the other case. So you have very strong structural changes, right?
Mm-hmm. Yes, this should be the case.
And so does this, because I could not see well, because surface charge are not exactly the same, does this correspond to the situation in figure 6.6 for the density profile? Yeah, I think it's the same. They are the same surface charge.
Oh yes, exactly. Yes, so this should correspond to this. Exactly. And I think it's the same, yeah. So purple corresponds to purple
Okay. And so the orange in this case looks very interesting because it's you have clearly two, in the case where you have the two peaks appearing in the density profile, so
yes.
Maybe one is not so defined, but
yeah.
Well, you have the first peak and you also have the second feature for sure.
Yeah.
And so I see that you looked for a kind of flex transition there. You did not see anything on you did not see any ordering transition, but do you see in this orange simulation, do you see some configurations where you have a lot of ions on the surface and some configurations where there are no ions? I mean, do you have two states or do you have a mix of the two?
I haven't looked into this much. This whole thing, this was supposed to be a manuscript, but it was too incomplete, so I put it in text instead. I haven't really looked into this that much, but what we saw was that. So we have this non-monotonic behavior again, right? With the magnitude of the overcharging and surface charge on this homotonic behavior. And then we saw that this insect is then the co-ions. That's the co-ions. And then we saw that when this inner layer, when this gets filled, this inner layer, then we have this opposite trend.
Yeah.
So it changes there. But yeah, I haven't really looked into the structures much more than this.
Yeah, it could be a kind of waiting transition because you have a wet state and
Yeah.
state.
Yeah, I mean, yeah, it looks like it here also. So yeah, this I should definitely look into more. Yes.
So since we are with a phase transition, we will switch to the part. So here, I think I was very interested by that one because I think that's clearly a topic where observing something from experiments only would be very difficult because they can experiments you can only like this microscopic properties, and this kind of transition can be hidden because you have an averaging effect on size of pores and so on. So maybe there are things happening that people miss, and this is where clearly simulations have an advantage because we have a good control of what we are looking at. And so that's something where I think we can bring some suggestions to experimenters to explore new systems. And in fact, especially this concentrated to direct regime is to put you some context that you may not know because it's coming from another community. This is a field where you can find some aqueous biphasic system. So it's more complex because you have two types of anions, for example. But when you are at high concentration, if the two anions both like water, but they don't like each other, you can form on one side an aqueous solution concentrated in the first salt, and on the other side an aqueous solution concentrated in the second salt. So you have this kind of phase transition occurring depending on the concentration. And this is the kind of thing that could lead to this kind of effect inside pores, but it's quite difficult to address for the moment. So my question is about, so you see this first order transition when you have a larger separation with what you call the constant science case, but not when you go towards smaller ones, smaller separation, 20 angstroms. I'm wondering whether there is a Phoenix size effect there, because for first order transition, you expect the effect to be seen when you increase the size of your system. So did you try this to increase the lateral size of the system to see if you start to have more hysteresis as in the case of 30 angstrom?
So this is the direction which is parallel to surfaces.
The size. Yeah, so you keep the same spacing between the two walls, but you double or quadruple the size of your system to see if you still have this crossover or whether you start to form first order transition.
So I know that in many cases we tried this. In this specific paper, I can't remember if we tried to make it larger. I want to say that we tried to like twice as large. We usually test a system that's twice as large. So I want to say that we did, but I can't remember if we actually did it. So yeah, unfortunately. Yeah. If we did not, it's a good thing to try definitely.
And then, so when you see a jump at the first order interposition, so you have 2 points in the two branches that are the same potential. So does it mean you have a simulation where the system is either one of the 2 states, or you have a simulation of the left and simulation of the right?
It's in either one of those.
Okay.
Yes.
And I guess, okay. There is no way to have a simulation where the system is jumping, well, to be exactly at the transition point and to see the 2.
No, not in this case. No, we have not. Then it's just it happens, and it happens pretty fast. So
Yes.
So you have a simulation, and then it happens pretty fast. There's that. When we do we have not seen that in these constant potential simulations.
But again, it's Monte Carlo, right?
Yes. Yes.
Because one could expect that, well, in molecular dynamics, if you fall on one side or the other, you're stuck, then it's almost impossible to go back. But in Monte Carlo, normally there could be a point where the 2 minima have the same probability and instead of jump onto the other. If you consider. And
No, I can't remember if you do that.
is there a way to, in fact, there are some surface charge that you cannot access here. Is there a way to add a constraint to the system to force it to sample this region?
The middle region.
Yes. Maybe so. Maybe, for example, in molecular dynamics, when we want to sample this kind of transition, we can add some harmonic potentials that would force the system to stay, where it doesn't want to be, basically.
Oh,
yeah. But I don't know whether in such case it would be easy to implement or not.
Yeah. I know there are of course bias in methods, but I can't think of how to constrain this because then you have to constrain the surface charge. Then.
Yes, or to maybe not to constrain, but to restrain, to bias it towards a given value.
Yeah, exactly. And since this is controlled by the grand canonical steps, so the insertion and deletions, you have to do something there, I guess.
Yes, well,
yeah, I can't think of anything.
Yeah, maybe. And then, of course, I was a bit confused by this constant psi non-conducting. Well, also this is quite a theoretical tool, right? It does not really correspond to the using of an experimental condition where this would happen.
Wait, what will happen?
So the constant psi non-conducting sigma.
Okay.
It looks a bit contradictory to me to have this, but I understand why you do it because it's way to have not very well to be the middle between the 2. But it looks contradictory at first.
Yeah, you mean just the fact that you have constant potential and non-conducting substrates. Yes. Yeah, I guess it's hard to experimentally realize.
No, I don't know. It's kind of theoretical tool. It's always very useful. Okay. So I think I'm almost done. Just as a bonus question, for which I really have no answer. Which is, so again, this part of during your presentation, you mentioned the negative capacitance. So what would be the physical meaning of negative capacitance?
That's a good question. So I tried to read up on it a bit, but there seems to be not much to. Yeah, it's a very good point. I mean, a physical, other than that, when you change the potential, you get an opposite change. So this was really important in the physical. Yeah, other than that, I don't know. But I know it's I read somewhere that if we can find such systems, like we can get this power dissipation in transistors, for instance, where you apply some potential over the gate, as it's called, and this has some capacitance. And this somehow, if we could find this negative capacitance, you can decrease the power dissipation in these transistors. But yeah, no. Other than increasing the potential, which is decreasing the surge, I don't know.
Yeah, I've seen in other contexts mentions of negative capacitance, but it was not the capacitance itself which was negative. There was a negative component. So, sometimes you can separate the capacitance into various contributions in series. And there are some DFT, actually DFT based paper where they study consumption. And then there can be some negative contribution. I think it's due to the charge transfer between the short rate in the molecule.
Okay.
But again, it's one component. The overall capacitance remains positive. So to go beyond that.
Yeah. It's still pretty unclear when this negative capacitance occurs, or under which conditions, or if it can occur.
Yeah, of course. In the constant same manufacturer are doing a bit what I was mentioning, which is to force the supercharge to be at the value.
Yes. Yeah.
So,
Yeah. Exactly. Yeah.
Okay. So I think thank you very much for your answers.
Yeah. Thank you for the discussion.
Thank you much for that. We just check the chat here. We have says anything. Okay, that's probably nothing important, but we can keep it up. We see if somebody asks a question that way also. Anyway, so like this. So now we have the big room microphone. So people not asking questions should not speak to anybody else, because you will be broadcasted live to the universe. But anyway, so we'll start now with questions from the committee. And please, Maria.
I think you have to push that so that they can see, so the Zoom people can see
this one, I think. I hope.
Oh, there's one. I don't know, maybe we should take this whole.
Yeah, the question is if the audience want to be viewed. Is anybody objecting to being streamed?
In front of millions of people.
Okay.
So first of all, thank you very much for the interesting discussion so far and this work. I'm going to start by a little bit of continuation of what Matthew Salan was asking as his first question. So I'm going to go to the Ionic models that you have. So you are using a model called restrictive primitive model for the ions in your system. And for the sake of audience, can you repeat what that model means?
So I think actually restricted primitive model, I think that's like when you have the cation and anion of equal size and equal charge. But then sometimes we have or often we have a multivalent counter ion, which is on the opposite side to the surface.
So these are essentially spherical ions
Yes.
which have a point charge in the middle.
Yes, 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 exactly.
This is a simplified ion model, so chemically ions are maybe a little bit more complex. How will your choice of model affect your results, and where is this relevant?
So hopefully the mechanisms that we have investigated, hopefully they will not change very much if you're not having a very, I mean, of course, if you have a very, very big bulky molecule with a monovalent charge, then of course it might change. But generally, we hope that the general trends are of course the same. And then if you want to do quantitative comparisons, or if you want to calculate the realistic values of things, maybe this is not the model that you would choose. I mean, if you want to get in the correct ballpark, so to speak, then it might work, but not for the quantitative analysis.
Are there some features that, for example, the spherical nature is losing?
Yeah, like it has no flexibility. It can change conformation during a simulation, of course, and then just the fact that it's not spherical in other areas.
Yeah, I'm also kind of like looking at ion polarizability, so charge redistribution due to other charges nearby. So
yes, this is of course also there's nothing like that. It's a central charge and it stays there, and it's a point for charge.
So for especially the multivalent ions, I would expect there to be quite a bit of asymmetric nature, so it's not perfectly spherical, and then there are going to be oriented configurations coming out.
Yes.
But yours is a very good kind of like first approximation of the ion cycle. Then maybe you have a background solvent. Does that make a difference for the outcome?
If we have it, or if we don't, as compared to not
having. You have now
having.
a continuum solvent in the model.
Yes. Yeah, so this changes, I mean, mainly the electrostatic coupling, right? It comes in via the dielectric constant. So it will decrease the electrostatic coupling. Yes. If that was what's your question?
Where would you consider that assumption to make a fault in your results, or make your results deviate from what is the actual reality?
So hopefully the interaction between, for instance, an ion and a surface is dominating even in a system with explicit solvent. So I mean, then our results would be the same, I guess, or the general trends at least. So yes, and now if there's water as a solvent. So yes, so I guess if it's high electrostatic coupling, then I guess it's a good approximation to not have water, because then the other interactions would be dominating the ion wall.
Yeah, the water does have a strong structure around the ions, so.
Yeah.
Okay. So then maybe going a little bit more into detail from the model. In your slit geometry setup, you observe with asymmetric solved correlations that lead to charge reversal. So by asymmetric, I mean that you have multivalent one type of ion and monovalent another type of ion. Just to put everyone on the same page, what are your anion and cation valencies and sizes?
So the sizes are I think, so we use different sizes, but I think most often we use 2.5 angstrom in radius.
So same size for both.
Yes, exactly. And then we used both a divalent counterion and a trivalent counterion. So yeah.
And there are co-ions as well, which are.
Yes, which are always monovalent.
Okay. How do you expect these choices to affect your results. So you see now charge reversal and you see charge distributions potentials.
Yes. So for in a symmetric salt, you would not see this charge reversal. So that you see when you have an asymmetric salt. So then that will be either you have a divalent counterion, or it will probably happen if you make the counterion much smaller, also much smaller. Yes.
So the effect is stronger for point ions, and then dye spendings are symmetric. Yeah, I agree. That's how it works. Okay. So that's the particle-based simulations. Then you also have the classical density functional theory model for the same thing. And there it's not so obvious how to put in the ions and their sizes. You had made a choice how to do that. Can you again elaborate for the audience how you did the ion sizes there?
Yes. So what we did was we included this what we call Coulomb holes between like charge species. So then you decrease the density around each ion. So then and I guess this is a measure of the size also then.
I assume that you are using some kind of functional form for that Coulomb form.
Yes, and I think
Was heavy.
I think we have it somewhere. Correlations. Yes, 5.10. Yes, 5.10. And also, and also on the next, so this was page 59, and then on page 60, you could also use this Heaviside step function.
So these are now, it's based on the Coulombic interaction, and then you have the hydration shell. In some cases of ions, there would be some kind of pressing around it. Is it possible to take into account in this kind of approach, more variety? Because you are now assuming a relatively small, rather localized ion. Can you modify that assumption?
So that depends on what you mean by modify, because we can include, it's easy to include another functional form of this Coulomb hole or whatever you want to call it. So this is very easy to modify this one.
How far can you follow the particle-based approach? Because the particle-based approach is going to be like the ion is there exactly, and it will move according to the Monte Carlo moves. Now you have a density expression, which has a penalty for the ions not being at certain location.
Mm-hmm.
Where do the differences start showing?
There's a lot of differences. I'm not sure if I understand your question.
So one model is based on a mean field theory, and then you add up like the localized ions there.
Yes.
The other one is particle-based, not mean field to begin with.
Yes.
And I'm asking how well does the mean field originating one, so how far does it come in this kind of ion? So this is a little bit out of my field. I'm much more on the particle-based models. So I'm asking how far can you get into description of the solved solutions?
I mean, you will not get away. I think you will not get away from this density description.
Yeah.
So this you will always have. So I guess, I mean, if I understand your question correct, like then I guess the closest you can come to this particle description is adding this. I think that we did, like you add this, for instance, the Heaviside step function or something. So if you have this radial distribution function, you cut it off close to each ion or something like that. So you would not, you will never come to this particle based approach. If it's, I hope it somewhat answers your question.
Yeah, it's an approximation. Yes. And you can modify it. Okay. Then you have the positively charged ions, the negatively charged ions. I assume that you are using two superposed densities for getting them. So one for the negative ions, the other one for the positive.
Yes.
Are there challenges in that one?
You solve them separately in this case.
So the challenges are at numerical level.
Yes.
Okay, can you comment on that?
I mean, so it goes much faster than a Monte Carlo simulation. Is that what you're after? Yeah, but do you mean to like
the convergence stability, or like how do you solve?
Yeah, so these are solved self-consistently. So we have you have a density that you start with, and then you put it into the and then you have an expression. Then you have this self-consistent expression to minimize the free energy. So you have your density, and then you put it into that expression, and then you get a new density, and then you put it in again, and then you continue like this until it's converged.
And there is some kind of linear combination involved, so
yes,
it's not directly. Okay.
Yes, exactly. Yeah, exactly. So so you combine with your last. Yes, exactly.
Then this is maybe going to detail level on figure 6.8. The figure is demonstrating this anomalous overcharging versus this surface charge response with surface charge. And then the first thing that I want to check that you are plotting the negative electrode cation induced apparent surface charge in that plot.
What did you say? I'm sorry.
So figure 6.8.
Yes.
The first thing that I want to check that this is the negative electrode cation induced apparent surface charge that is being plotted.
Yes. Yes.
Okay. So this is a curious question. How do you define this apparent surface charge?
So this
because
is,
it's in many places in your thesis.
Yes, yeah, and I might have forgotten to do that, which was a mistake. But this is the integrated charge. So you start from the surface with the surface charge, and then you integrate the in the direction normal to the surface into the you integrate the charge. So the salt. So yes, so it's just the integral in the direction inwards towards the middle of the box.
How far do you integrate to get the surface charge?
So here we integrate always to the middle of the box, because it will be, since we have equally charged surfaces, it will be completely symmetric. So in the middle here, which says -50, this is the middle of the box.
But then what is the y-axis, the apparent surface charge?
This is the integrated charge. So this will, if I would have plotted this, if I would have increased the y-axis downwards, so to speak, so that I can see more negative values, then each of these lines would start from the surface charge.
Okay, so it's so that's just the expression of how the system charge is, and because you are not showing the entire curves, then I don't see where it's coming. Okay.
Yes.
Okay.
Yes.
Okay. Fine. So then Looking at this data, this may also be now that the axis is cut. It doesn't seem to me that the curves are starting from the same location. Yet, if I understood correctly what you're writing, the ions are same size.
Yes.
Would you elaborate on why the curves look like that?
Yeah, okay. Yeah, so you mean that the maximas are shifted.
And also the starting location. Because if these are same sized ions, they should be able to approach the surface to the same location.
Yes. I mean, this could be related to what we discussed earlier about these different layers that are filled, but these shifts are not very large. So, but let me see. So the blue one, yeah. I don't know in this case because it looks like the blue one is the one that's closest, or it has the lowest surface charge. It's also quite small. It's not as large as the other ones. But I guess it has to do with this layering somehow. Anyways, because if we look at figure 6.3, this is more like what you would expect, that it looks like it gets a bit closer. The maximas are drawn towards the surface with decreasing surface charge. So at a strong surface charge, you're very close to the surface, and with the maxima, it's very close to the surface. But then in 6.8, you have this strange trend happening where the magnitude of the overcharge is a non-monotonic function of the surface charge. So yeah, if we start with the blue one, which has a low surface or the highest surface charge, yeah, and then you go in the direction towards lower surface charge. You can see that it's non-monotonic. So I guess it has to do with this, and this we think also has to do with how the counter ions behave close to the surface. So it probably has to do with this.
Yeah, it's anyway very interesting, like where the peak positions are and where the curves start from. And
yes.
Yeah. Thanks. I think I would still want to talk a little bit about the hysteresis. So in the last manuscript, there was already discussion about this. So to me, this appears like a relatively simplistic model. So there are these point or spherical ions which move according to the grand canonical Monte Carlo, and it seems that it's taking one path going up, one path going down.
Yes.
Could you elaborate how your Monte Carlo moves are, and what kind behind this is that can you be stuck in one region of your simulation set?
Yes. So the way that we did this is that if we start with a very low surface charge, so very negative surface charge, then we will end up in this dense phase. And then if we start, on the other hand, with a very high surface charge or a surface charge close to zero, then we will end up in this dilute phase. And then we can, if I start from this dilute phase, and I'm kind of careful about and changing my and then I run multiple simulations. So I start from this dense phase or this dilute phase, and then I change the potential a little bit, and then I will continue to be in this dilute phase until the surface charge is low enough, and then I just jump. And this is the same case for this dense phase, that I start in the dense phase, and then I start in the dense phase at some surface potential, and then I change the surface potential a little bit, and I start from this dense phase, and then I can continue on this purple one.
But your moves are such that you could transfer from the dense phase to the dilute phase.
Yes, yeah, exactly. Yeah. So we have these grand canonical steps. So yes, so this could, and also this happens at the top purple point. This exact thing happens, right? There we have in one simulation, it goes there. I start from the dense phase, but when the simulation has converged, I'm in the dilute phase.
Did you check what is the temperature effect on this response?
No, we did not. I think no, because we. I mean, if it will change if we change the temperature, then we will get another. This will probably shift. This hysteresis will shift in the surface charge.
I've taken some time, so thank you. I'm gonna move.
Thank you.
Okay, thank you for a nice discussion and a very nice thesis. I especially like your image charge Ewald trick, and I would like to discuss image charges for a little bit. So there's one statement on page 42 that I would like you to sort of discuss a bit. So it says, one might think that the treatment of non-conducting surfaces in simulations would be simpler than for conducting surfaces. After all, in such systems, there are no image charges to take into account. Is this completely accurate? As in, is image charges a feature of conducting systems? Where do image charges arise?
I mean, they arise. So when you have a polarization, we can describe this polarization with the image charges. So if there's no polarization, I would say that there's no image charges.
But you have, in your case, so if you can draw the figure 3.6, you have polarization, it's on page 39. You have polarization both on your right-hand side and on your left-hand side, right? You just have polarization to different polarizations, to different polarizabilities for epsilons, right?
Yes, yes. Yeah. But when I say, okay, so non-conducting surfaces, then I mean, so then I mean that the dielectric constant is 0. So it's vacuum. And then I would say there's no image charges.
Not quite, but getting closer. So first of all, which epsilon is vacuum?
1.
Yes.
So this
is and if you have, so can I ask you to draw on the board? So if you draw that figure in 3.6, but for general epsilon on the left-hand side. So if you call epsilon 1 and epsilon 2, yes. In general, your real charge is on the right-hand side. So if you call that Q, then there is a general formula for the size of Q prime, which is the charge on the left-hand side. So your image charge.
Yes.
I mean,
it's like E.
Does this sound familiar?
Yes, it's like E2 plus E1 is like E2 minus E1. Sounds like this.
Reverse that.
So like this.
And what sign do you think you have? If you so start by epsilon. So sorry, in your conducting case, epsilon 2 is what? So which case is it that you have treated in your?
Okay. So this is infinity.
Yeah, and what's epsilon 1?
Okay, so this it should be epsilon 1 is, I don't know, whatever is it, or 78 maybe.
Presumably, yeah. 80-ish.
Yeah.
So if your Q prime equals minus that, then what do you get for?
I should. Yeah, this maybe it should be like this.
Yes, there is a minus sign in front.
like this.
Yes. So indeed, if you have epsilon2 equal to infinity, what do you get then?
Then you get -1.
Yes.
Epsilon 2, yes.
Q prime.
Yeah,
well,
yeah,
it
yeah,
will
yeah,
also
yeah.
be Q in front of the ratio there, right?
Yes.
So you get Q prime equals to minus Q.
Yes, yes.
Which is the case you have considered, right? So the image charge is equal and opposite of the real charge.
Yes, but if it's 1, yeah, it's
What? Now you should be epsilon to minus epsilon 1 in the top. It should be a,
where should it be?
at the top, and that one should be a minus sign.
This one.
Yes. It should just be minus sign. Now it's correct.
Okay, okay.
Yes. So
Oh, yeah.
what if you have a vacuum?
Yeah. Yeah. Then you
What
have.
do you get?
Then you have 1 there. Yeah. This is. This I'm a bit confused now. If I'm being honest.
Yeah. But so what would you insert there if you have a vacuum on the left hand side?
I will insert 1 here.
Yes.
And I will put
So
1
so
there.
if you just write it down, so 1 minus
-1 minus 1 plus like this.
yeah, and you have epsilon 1 equal to 80.
Yeah.
Ish. Then you get
Okay, so you get
something on the order of
not said at least 79 minus 81.
yeah, which is 1.
Yeah, close to 1.
So, but not with the minus sign, right? So it's
Yeah.
So indeed, you get then Q prime equal to roughly
1.
well.
Or yeah,
Q.
equal to equal to.
So you get an image charge,
Yes.
but it has the same sign as and almost the same magnitude as the original charge.
Yes.
So if you want to simulate a system where you have vacuum, I mean, so what is it that you've simulated when you say that you have non-conducting boundaries in paper?
I mean, non-conducting, then we have vacuum actually. There's nothing there.
No, but you don't, right? So what you have is, if you look at that equation, if you just ignore the image charges, what does it correspond to?
Yeah, I mean, I agree, but still I don't have anything there in my simulation.
No, but not having anything there means having the same dielectric constant outside as inside. It doesn't correspond to having a vacuum.
Oh, yeah.
Electrostatically, that's my point.
Yes, okay. Yes, okay.
So when you say non-conducting, you mean no dielectric discontinuity,
Yes.
which is not the same as vacuum.
Yes, you are. Yes.
So if you would want to simulate a vacuum, as in so figure 3.9, for example, on page 42, could you not do that with your nice trick? Instead of using slab Ewald, because if you do slab Ewald, you'll have no image charges, right?
Yes.
So you're not actually simulating vacuum.
Yes. Yeah. I mean, yeah.
So how would you do that with your trick?
Yeah, you could definitely do it. You just do the same thing, but you don't invert the charges.
Precisely. Well, you couldn't do it with fractional charge, like 79/81 would be hard, but if you approximate that to 1, then would you see any problems implementing and
No, not if it's 1. No, I wouldn't see any problem.
I mean, you would not be able to use single ion insertions anymore,
True.
right?
Yes,
Because
yes,
electroneutrality would need to be maintained in a central box.
Yeah, this is true.
But yeah, so this is, I think this is seems like a detail point, but I think it's
but it's a consistent
important
error from my side. So it's a
point that vacuum is not the absence of image charges.
Yes. This is a very good point, and I have confused myself. Yes.
It's an easy confusion.
Yeah.
So I have thanks for settling this. So I have one other slightly shorter question. So on page 100, on paper 3, there is a statement that let's see where is it. So at the top left column, we note that in stability studies, the systems are canonical. That is, there is no infinitely large bulk solution from or to which additional charge can be added.
Yes.
So from what I remember from statistical mechanics, I always teach that ensembles is a theoretical concept which you use for mathematical or computational convenience, but it's in experiments they should all, I mean, when you go to the thermodynamic limit, the choice of ensemble doesn't matter. So it's not an experimental concept. So when you say that an experiment is done in the canonical ensemble, is that, can you elaborate on that? Because many computer simulations of stability studies is based on grand canonical simulations, right? You have two walls, and then you transfer those force curves to colloidal stability. But it sounds here as if you can't do that because experiments are not.
Yeah, I mean, I think it is these specific experiments that we mean. So in these experiments, they had, I think they had these very highly charged, ions, I think, and there you add exactly the amount of ions that you need, right, to neutralize. But yeah, I have also been a bit confused by this.
How do they?
Because yeah, I mean, because then the difference from AFM, where you have some kind of where you have some kind of a needle or a surface somewhere, and you have this bath of ions, right? So this would be truly grand canonical, I guess, because you have this infinite bath. But then in this, yeah, I don't know. I don't know. Really.
But I mean, but even for a low concentration, you can see the.
Yeah.
I mean, the question is whether the bulk is infinitely large, not how big its concentration is, right?
Yeah. Yeah.
So, because here it sounds like it just have a very small system, but having a low concentration of salt in the bulk is completely allowed.
Yeah, I agree. I agree. I agree. Yes, I agree. Yeah, no, I don't have any good question for this or good answer for this, unfortunately.
Okay, no, I found that a statement that I didn't fully follow, but
I will think about this again.
Okay, I think in the interest of time, I have a long list of questions, so we can discuss them over coffee. So thank you so much for a good discussion.
Okay, thank you. In a way, it's comforting, but it's also a bit tricky that we have been asking the same questions, or I had a long list here. Well, a short long list, but it's good to have these discussions in the sake of time. But I still want to begin by saying that it's been a very interesting thesis to read. I like the careful analysis that I think you have been doing, investigating things in proper detail, which appeals to me. Having said that, perhaps one more proofreading could have been in place, especially for the summary and the last manuscript, but it's okay. But let's say that in your summary on page 45, you say there are two types of simulations. There are classical simulations like Monte Carlo simulations or Metropolis chain Monte Carlo and molecular dynamics. And then there are also those aimed at solving the Schrödinger equation, such as the Fock. What do you mean by simulations? And would you not call the solving of the Schrödinger equation a calculation rather than a simulation, unless you do wave packets or something?
So what did I write? Did I write simulation or did I?
Yeah, two types of simulations you wrote.
Yeah. I think this is kind of a fine line always if you call it a simulation or a calculation. I mean, I think it's quite clear that for instance a molecular dynamics, that's a simulation, I would say, because then
no, my question was really when you wrote that solving the Schrödinger equation is a type of the first type of simulations.
Yeah.
I'm just curious how you define a simulation.
Yeah. Okay. I get your point. This is true. I mean more like simulations that are based on this approach of solving this equation in contrast to Newton's equation of motions, or Newton's equation of motion. This is what I meant. It was a poor wording.
And then also in your, I think at the end of some chapter here, you had a paragraph on correlation functions as a mean to test, or how often you should write your trajectories during, coordinates during trajectory. Since you have included this in your summary, did you actually try it?
Yes.
Okay.
But not every.
No. But
this is something I did in the beginning. Yeah. Because out of curiosity.
Very good. Very good. I was just curious because it wasn't clear to me whether you tested it or not. Yeah. But that was very good.
Yeah, and I know it's very uncommon to do this in practice.
Okay, I will skip that one. And maybe I can ask, there are different ways to treat electrostatic interactions in simulations. Is the Ewald summation?
Yes.
Very common one. There are also other ways like multiple expansions or spherical boundary conditions and alternative numerical methods. I mean, one is has been described by Lichner and Sperp in Zurich, for instance. Why would you use the Ewald summation specifically?
So it's
what's the rationale behind using especially this one?
Yeah, so it has a lot of potential for optimization. It has been optimized a lot, so it can be. I mean, it is theoretically infinite. I mean, you can sum very large systems, and you can do it pretty fast also. So I guess this is the main reason that it's used. That it's you get these large interactions or these long range interactions. You get it fast.
Okay.
I would say this is the main reason.
But I'm just curious behind the choice of method, so to speak. It's the most common one. Yeah, I don't doubt that at all. I mean, I agree with that, but just to have to convince yourself by the method you use, actually. So, you had another statement in. Yes. Okay. So on the second page, on paper 2, which is 90 in your thesis, it says that, if I may quote approximately, in the direction parallel to the surfaces, the periodicity may induce crystal artifacts, but using isotropic periodic boundary conditions in these directions, such effect can be mitigated. And you wrote that in our simulations, however, we did not use isotropic boundary conditions. Could you just briefly describe what is meant by isotropic boundary conditions and why they would reduce this effect?
Yes. So why we wrote this is because when we use this method, we get this periodicity in the direction normal to the surfaces. This is what we want because this is the exact solution that we want with the image. But then we have the normal Ewald problem in the other directions that we get this infinite crystal. But then there has been, and then we cite a method here also, I believe, which reduces this periodicity or this crystal effect. Yes. And I'm not very it was a long time ago since I wrote about this method, so I don't really know how it works for the technical details.
I was just curious. let's see if I can have one more question then. I had one. Okay, this has been asked. And yeah, you have what you believe are the most interesting, you can say unexpected, but interesting and results in your thesis. What do you find yourself being most interesting? It's a hard question to answer.
I think everything is interesting.
What are you most proud of?
Yeah, I mean, I thought the last paper, I enjoyed like looking at those results and analyzing those results and running those simulations. I enjoyed, but I also really enjoyed the first and the second paper, which was more method development. I also really enjoyed those. So yeah, I don't know. I would say it's a tie between the method development and the last paper.
So you had fun most of the time.
Yes, exactly. Yeah, yes, I did.
I did have a question about which the method, if you think they become standard methods in different big packages 5 years from now on, and but I think the opponent has already asked that question, so I'm happy with these questions. So
Okay.
thank you.
Thank you very much. Thank you, all members of the committee, for your questions. So we will see if we have any. We'll go back to me, I think. So we'll see if I have any questions online. No, I can't see any questions by email. So then we'll ask the audience here. Are there any questions in the auditorium? You have a chance. The question: what does it all mean? Okay, no one.
I have one question.
Yep, good.
Maybe I can cool down because it takes a little bit of time.
Yeah, sure. I can imagine. I will stand up because I'm almost about to pee my pants. I have to walk around a bit.
Can I ask you to open up Slack or email?
Select. Do I have to do it on a computer?
On this one preferably, because I need.
Because I don't have internet on my computer.
Ah.
Oh, okay. I will share from my phone. I will share internet.
There's no internet on this one, or?
Yes, but this is not mine.
But we can do it from here also.
But I'm not logged in and stuff. I mean, and I can't remember my
otherwise
password.
you can just. Okay, otherwise I can log into mine. Actually,
okay.
It's fine. Let's see.
I have this autofill password, so
I see. I think I remember mine. Let's see. Maybe not.
Work? No.
Okay, so let's go.
Okay,
to
but
my-
maybe because this
Remember.
Slack I don't know, but this I might know this actually. Yes. What now is Lund, right? Only Lund.se. What is at what? LU. I already forgot.
Yeah.
Oh yes.
Perfect. And then you should have one email called Sifferfrågan. Maybe download that.
Okay. What did I do?
I hope they have Keynote on this computer, but
Oof.
then
this
is not as bad as it looks.
This is
so.
complicated.
Let's see.
Then
So
we should share.
I should also
data.
share it, yeah. Yeah, on Zoom,
Oh, okay.
right? So
I'm
let's
really
see.
nervous.
Is it this one? No.
No.
There. Okay. Share screen. And this one. Okay, and then play there. Now I hope it's visible for everyone.
Yes.
So, okay. Hello, everyone. My name is Ivan Appelsin, and I'm actually here from the Skåne Employment Service because it has come to our knowledge that you're just about to be finished with your PhD.
Yes,
is that correct?
This is true. Yes.
Okay,
yes, it's very
perfect.
true.
Because then I have some very important information. It's namely so that you're presumably you will stay here in Skåne and look for jobs, right?
Yes. Yes.
Yes. So at Skåne Employment Service, we've just introduced this new course called Skånska for Programmers, because this is something that's turned out to be very important at the working places around Skåne. So it's an introductory course in programming lingo commonly used at working places around Skåne. And it's actually starting already next week. The problem is that there's another course that you need to pass to join this programming for Skånska, and that's called Git på Skånska. So yes, Git på Skånska. So after a fast check on the job market, actually 21 out of 27 jobs require this Skånska for programmers. So I'm here to sort of increase your chances to succeed on the job market.
I'm very happy for it.
So the goal for today is that you will pass this. And the whole job market will sort of open up for you.
Okay.
So your full potential can come to use. You know.
I'm super excited.
Yes. Yeah. So what I've done today is to prepare this course in a very sort of condensed format. So it's a 7-question quiz. Passing grade is 50%. And just because you have done an amazing job on the thesis and performed very well today, I'm so kind to actually give you a lifeline also. So if there's some question that you feel you cannot answer, you can reach out to the audience and please pick the
right person or what? Choose carefully.
Yes, choose carefully, yes. And then they will answer the question for you.
Okay,
so,
okay.
One lifeline.
And they know the answer then, or what?
No,
Oh, okay.
I don't think, well, maybe some people,
know.
but
yeah.
you will sort of, go on feeling, So first, are you ready?
Yeah.
First question. So how do you actually type it in Skånska? Is it A, skjuta, B, fubik, or C, klydda?
Oh, this is. I say A, hutta.
Hutta.
Yeah.
Okay. It was actually fubik.
What?
So I'm sorry, but not correct.
Okay. I can still make it, right?
Yeah, it's 7 questions, so definitely. So question 2, fill in the blank. Så kan du asa spågen jag just nimmade och präga den till GitHub. So the word we're looking for is präga.
And push. Can you push?
See, correct.
Oh, yes.
Good job. Yes. So question 3, fill in the blank again. Skicka en jidder när du är färdig med kryddandet. Send me a what is jidder?
When you're done with the merging, send me.
You can also get a clue from the length of the line. Actually, it's not a very short word.
Send me a message, but it doesn't sound very programmy.
Do you know any? Think of Git if you think of Git commands.
But what do you do after when you're done with the merging? You send a pull request, or
yes, that is correct.
Oh, yeah, okay.
That is correct.
Perfect. Okay, so 2 out of 3.
Very good.
Very good in this also. Yes.
Question 4. What does UD mean?
UD. Can you say it in Skånska?
UD.
UD. Okay. Now it makes sense. B, is it? No, C, repository. SIC repository.
It was remote.
So close. 2 out of 4.
2 out of 4. Question 5. What does hutta mean?
Oh, but this was in the beginning, right? No, I was wrong. Right? Oh, what was the first question? I can't remember.
I think it was an option in the beginning. Yeah.
So commit. I say commit C.
C. Correct.
Oh, yes. Yes.
Good. So 3 out of 5, right?
If you add new file, you should. Oh, this is a hard one. This is a very hard one. Can you say the different options?
Fubik also files, Fubik Kaugerhus files, or Fubik Tokka files.
Oof. So it can't be C again. I mean, this is.
Could be C, but
it can't be again. I mean, it was last time. Right? I mean, it has to be A.
It's random.
It has to be A. Also. Yes.
Correct. So last question.
Oh, but it has to be B, right? Slöda. Fubik slöda.
See. It was Tokka. So let's see. After, if I'm correct, you have 4 out of 7 questions, correct?
Yeah, that sounds
correct. Yeah. So let's look at the grading matrix. So if you would have had a score of 2 or less out of 7, you would actually be yourself a Fubik, and that would be a fail. But luckily enough, you got more than that. You actually got 4 out of 7. So impressive job.
Oh, thank you.
Yeah.
My first attempt also.
You have passed actually.
Oh no,
Very good job.
you.
Yeah.
So the job market is now open.
Yes, it is open.
Perfect.
And as a token of appreciation, you will now get this certificate of completion, which will actually serve as your entry ticket to the course.
This is fantastic.
And you can put that on your desk in your new office and show that you really know this.
Give it up. Let's see. Yeah, thank you.
Very good.
Thank you very much. This is the best prize.
Yes, it's very honorable.